normal mode, airplane yaw control characteristics are similar to conventional airplanes. Unlike conventional airplanes, the rudder pedals do not directly position the rudder surface in flight. Instead, the pedals command a sideslip maneuver, with the airplane's sideslip angle dependent on pedal displacement. The flight control system will then position the rudder to generate the commanded maneuver. The system constantly monitors airplane response to pilot inputs and repositions the rudder as necessary. Pedal forces increase as pedal displacement increases. These forces do not change with airspeed changes. A rudder ratio changer automatically reduces the sideslip command for a given pedal input as airspeed increases. Sufficient rudder authority is provided at all airspeeds to maintain airplane control in engine failure conditions and during takeoffs and landings in crosswind. Airplane yaw control in the secondary and direct flight control modes differs from normal mode. The flight control system continues to receive and process pilot control inputs using simplified computations to generate flight control surface commands. The rudder pedals command a proportional rudder deflection instead of a maneuver command. Pedal feel forces are unchanged from normal mode, but rudder response is slightly different. In secondary and direct modes, the rudder ratio changer is based on flap position. With flaps up, the rudder response to pedal inputs is less than the response when the flaps are not up. In the secondary and direct modes, gust suppression is inoperative. Asymmetry compensation is inoperative. Flight envelope protection is inoperative. And yaw damping is degraded. Manual rudder trim operation is provided in all three flight control modes by a rudder trim selector located on the aft aisle stand. Two rudder trim rates are available. A low rate is commanded with the selector rotated to the detent, and a high rate is commanded when rotated past the detent. To provide pilot awareness, the pedals move to reflect the amount of manual rudder trim applied. When ground speed exceeds 30 knots during the takeoff roll, manual trim inputs are automatically zeroed, and further manual trim inputs are inhibited until in the air. Manual rudder trim is also inhibited with the autopilot yaw engaged on approach. Automatic rudder trim is provided in the normal flight control mode. To provide pilot awareness, the system automatically moves the rudder pedals to reflect the rudder position being commanded. This trim position is also shown on the rudder trim indicator and flight control synoptic. If the rudder deflection is minimal, the rudder trim remains centered. This prevents running the trim for normal situations, such as to coordinate a turn. On landing, automatic and manual rudder trim inputs are zeroed, so they do not provide a yaw command when the airplane transitions from the air mode to the ground mode. Rudder trim is displayed on ICAS and the flight control's synoptic. The indication on the synoptic is constantly displayed. The ICAS indication is displayed on the ground at power up and after landing if ground speed is less than 40 knots. The indication will also display in the air when any of the following ICAS messages are active: engine fail, left or right; engine shutdown, left or right; engine thrust, left or right; flight control mode; or primary flight computers. The ICAS indication normally blanks when either of the following conditions are satisfied. Gear up for 10 seconds, or 60 seconds after liftoff. A digital readout displays rudder position in 0.2 increments from 0 to 1 unit of trim and in 0.5 increments between 1 and 17 units of trim. An L or R is displayed to the left or right of the box for any non-zero rudder trim. A corresponding pointer position is displayed on the line scale below. When the rudder signal is not present or is invalid, the digital readout, left-right indication, and pointer are not displayed. When the rudder trim is inoperative, the digital readout is replaced with an X. Additionally, the box, the X, and the pointer display amber. The pointer will remain on the scale at the last known trim position. The flight control system attempts to maintain a zero yaw rate by automatically adding rudder corrections during reverse thrust asymmetry conditions or takeoffs in crosswind or gusty conditions. Under these conditions, the rudder pedals do not move, allowing the pilot to provide additional inputs to maintain directional control. On the ground above 60 knots ground speed, the flight control system attempts to maintain a yaw rate near zero by commanding rudder to counter the majority of the yawing moment due to an engine failure. The capability to counter a thrust asymmetry is an inherent part of the flight control system. The pilot can still recognize the initial onset of an engine failure through the airplane yaw cue, since the flight controls do not counter all of the yawing moment. Under these conditions, the rudder pedals move, giving feedback to the pilot that the system is working to counter a thrust asymmetry. In flight, when a roll or yaw asymmetry condition exists for any reason, the flight control system attempts to maintain zero roll rate and side slip. An automatic rudder input counters the yawing moment, and an automatic lateral control input counters the rolling moment. Under these conditions, the rudder pedals move to give the pilot awareness of the automatic function. The resulting rudder trim indication is automatically shown on the ICAS display. After the initial inputs, the system offloads any steady-state lateral control input to the rudder, resulting in a small side slip. Since the offload increases side slip on the airplane, the offload has limits based on the severity of the asymmetry. For large asymmetry conditions, a greater side slip is permitted, but some automatic lateral control input may remain after the offload stops. When this occurs, the ICAS caution message Roll Yaw Asymmetry is displayed. For severe asymmetric conditions, the ICAS caution message Roll Left, Right Authority is displayed to inform the crew of the limited roll control available. Automatic lateral and rudder inputs are only available in the normal flight control mode. They can be overridden by manual control wheel or rudder pedal inputs. The wheel-to-rudder cross-tie reduces maximum side slip and vertical fin loads by displacing the rudder in response to control wheel input. This function is available in the secondary and direct modes. In the normal mode, wheel-to-rudder cross-tie is not required. The flight control system automatically controls side slip and fin loads. In the normal mode, the roll and yaw control laws provide turn coordination and Dutch roll damping. The flaps and slats are high-lift devices that increase wing lift and decrease stall speed during takeoff, approach, and landing. The airplane has one inboard and one outboard flap on the trailing edge of each wing, and one inboard and 5 outboard slats on the leading edge. A 2-position Kruger flap provides a seal between the inboard slat and the engine nacelle on each wing. In the flap's 1 position, only the slats move. Flaps 5, 10, 15, 17, 18, and 20 are takeoff flap positions. Flaps 25 and 30 are landing flaps positions. Flaps 20 can also be used for some non-normal landing conditions. To protect against inadvertent deployment during cruise, flap and slat extension from the up position is inhibited when speed is more than 260 knots indicated airspeed, or altitude is above approximately 20,000 feet. This protection is only available in primary and secondary flap and slat modes. There are 3 modes of flap and slat operation: primary, secondary, and alternate. In the primary mode, the flaps and slats are controlled together and positioned using center hydraulic system motors. The secondary mode is automatically selected when any of the following conditions occur: the center hydraulic system fails, the control surfaces travel at less than 50% of the normal hydraulic rate, a flap or slat disagree is detected, a flap or slat primary control failure occurs, a primary mode fails to move the flaps or slats to the selected position, or uncommanded flap or slat motion is detected. In the secondary mode, the flaps and slats are controlled separately and positioned using hydraulic or electric motors. For example, if the slat's hydraulic control fails, the flaps are still driven hydraulically, but the slats are now powered electrically. Flaps and slats are still controlled through the flap lever, but operation in secondary mode is procedurally limited to flaps 20. The alternate mode must be manually selected using the alternate flaps arm switch. Using the alternate flaps arm switch, arms the alternate flap control mode, arms the alternate flaps selector, disables primary and secondary flap slat mode operation, asymmetry skew and uncommanded motion protection, slat auto gap, and flaps slat load relief are not available, and disables the flap lever. Once in alternate mode, the 3-position alternate flap selector is used to extend and retract the flaps and slats. Moving the alternate flaps selector to extension causes the flaps and slats to extend simultaneously. Alternate mode flap and slat extension is limited to the slat's middle position and flaps 20. When the alternate flap selector is moved to retraction, the flaps retract before slat retraction begins. Flap position indications are displayed on the primary ICAST display. In primary mode, a single vertical indicator displays combined flap and slat position. The position commanded by the flap lever is also displayed. 10 seconds after all flaps and slats are up, the entire indication is no longer displayed. An expanded flap and slat position indication is displayed automatically when flap slat control is in the secondary or alternate mode, or any non-normal condition is detected. In the alternate mode, the position commanded by the flap lever is replaced by flap position index marks at all flap and slat positions, and numbers at flaps 5 and flaps 20. The index marks are used as a guide to position the flaps to the desired setting. When the flap lever is in the up detent, all flaps and slats are commanded to the retracted position. Moving the flap lever aft allows selection of flap detent positions 1, 5, 10, 15, 17, 18, 20, 25, and 30. The flaps and slats sequence so that the slats extend first and retract last. Starting from flaps up, selection of flaps 1 commands the slats to move to the middle position. The flaps remain retracted. Selection of the flaps 5, 10, 15, 17, 18, and 20 positions commands the flaps to move to the position selected. The slats remain in the middle position. Selection of flaps 25 commands the slats to move to the fully extended position. The flaps do not move. Selection of flaps 30 commands the flaps to extend to the primary landing position. During retraction, flap and slat sequencing is reversed. The mechanical gate at the flaps 20 detent prevents inadvertent retraction of the flaps past the go-around flap setting. The mechanical gate at flaps 1 prevents inadvertent retraction of the slats past the middle position. Flap load relief is available only in the primary mode. The flap load relief system protects the flaps from excessive air loads. If flap airspeed placard limits are exceeded with the flaps in the 15 through 30 position, load relief is displayed, and the flaps automatically retract to a safe position appropriate to the airspeed. Load relief retraction is limited to flaps 5. When airspeed is reduced, the flaps automatically re-extend as airspeed allows. Re-extension is limited to the commanded flap position. The flap lever does not move during flap load relief operation. Slat load relief is only available in the secondary mode. If airspeed exceeds 240 knots with the slats fully extended, load relief is displayed, and the slats retract to the middle position. When the airspeed is below 225 knots, the slats are driven to their extend position. The slat auto gap function is only available in primary mode when the slats are in the middle position and the airspeed is below 240 knots. At a high angle of attack, auto gap fully extends the slats to increase the wing camber. This will increase lift and the margin to stall. Once the angle of attack decreases, the slats return to the middle position. The auto gap trip threshold is a function of angle of attack, airspeed, and flap position. In the secondary mode, the system is too slow to respond to an auto gap request, so the pre-gap function is used. The slats automatically move to the fully extended position from the middle position when the flap lever is not up and airspeed is less than 240 knots. The slats remain in the extended position until the flap lever is in the up position or airspeed is above 240 knots. Cruise flaps improve the airplane's cruise performance by symmetrically moving the flaps, ailerons, flaperons, and spoilers based on airplane parameters such as weight, airspeed, and altitude. Symmetrically moving the appropriate control surfaces varies the camber of the wing, thereby reducing drag. Control surface movements are minor and no pilot interaction is required. Cruise flaps are only available in the normal mode, above 25,000 feet, and between 0.54 and 0.87 Mach. If the system fails with the flaps in an increased drag condition, the ICAS advisory message "Cruise Flaps System" is displayed. In primary and secondary modes, the flap and slat systems are designed to shut down when a skew condition or asymmetric deployment is detected. When the system is shut down, the corresponding ICAS caution message, "Flaps Drive" or "Slats Drive" is displayed. Uncommanded motion is detected when the flaps or slats move away from the commanded position, continue to move after reaching a commanded position, or move in a direction opposite to that commanded. If the flap or slat is operating in the primary mode, uncommanded motion causes an automatic transfer to the secondary mode, and the ICAS caution message "Flaps Primary Fail" or "Slats Primary Fail" to display. If motion continues, the system shuts down, and the ICAS caution message "Flaps Drive" or "Slats Drive" is displayed. A disagree is detected when, after a commanded input, the flaps or slats do not move or move too slowly. If the flap or slat is operating in the primary mode and the rate of motion is less than half the normal rate, an automatic transfer to the secondary mode occurs, and the ICAS caution message "Flaps Primary Fail" or "Slats Primary Fail" is displayed. If motion continues at less than half the normal rate, the system shuts down, and the ICAS caution message "Flaps Drive" or "Slats Drive" is displayed. The upper surface of each wing contains 4 sets of spoilers outboard of the flaperons and 3 sets of spoilers inboard of the flaperons. The spoilers are numbered from left to right, 1 through 14. Spoilers on opposing wings are symmetrically paired. Spoiler panels are used in flight and on the ground as speed brakes to increase drag and reduce lift. The spoilers also supplement roll control in response to control wheel commands. All 3 hydraulic systems supply 5 pairs of spoilers. Each hydraulic system is dedicated to a different set of spoiler pairs to provide isolation and maintain symmetric operation in the event of hydraulic system failure. The remaining 2 spoiler pairs are individually powered by 2 electrical buses. The ICAS advisory message "Spoilers" will display when 2 spoiler panels fail in the air, or 1 not down and locked spoiler panel fails on the ground. If 3 or more spoiler panels fail, the ICAS advisory message "Spoiler Pairs" will display. The speed brake spoilers are controlled by the speed brake lever located on the control stand. The speed brake lever has 3 marked positions: down, armed, and up. The speed brake lever can be placed in intermediate positions between armed and up. In the armed position, the spoilers extend and the speed brake lever is driven aft to the up position on landing when the main gear trucks untilt and both thrust levers are not in the takeoff range. When the speed brake lever is not in the armed position, the spoilers still automatically extend, and the speed brake lever is driven to the up position when on the ground with ground speed above 85 knots and either thrust lever was previously in the takeoff range before both thrust levers are moved to the idle range, or on the ground and both thrust reverse levers are moved to the reverse idle detent. The spoilers automatically retract and the speed brake lever is driven forward to the down position when on the ground and either thrust lever is moved to the takeoff range, on the ground and there is a transition to in the air, or in the air and either thrust lever is beyond 90% full travel. The auto-drag function operates by deflecting the ailerons downward and raising the two most outboard spoilers while maintaining airspeed. Auto-drag is used to assist in glide slope, glide path capture when the airplane is above the vertical path. Auto-drag only functions when, in the landing configuration, flaps are at 25 or 30, and thrust levers are at idle. Below 500 feet AGL, the auto-drag surface deflection is gradually removed so flare and touchdown are not affected. This function is active during automatic or manual approaches.